All right, so hi everybody. My name is Jonas Wulff, and I'm going to show you how we could, or how we can use Blender and Sintel to actually push research in the area of computer vision. So in that sense, it's kind of the opposite talk to the talk here and Sergey gave, because they had the computer vision within Blender, and here I'm going to talk about how we can use Blender to push computer vision outside of Blender. Before I begin, this is joint work with Daniel Butler from the University of Washington, Garrett Stanley from Georgia Tech, and Michael Black, who is my PhD supervisor at the Max Planck Institute for Intelligent Systems in Germany, in Tübingen, a little south of Stuttgart. Our institute basically does research on synthetic systems in the world and how they act, how they learn, and how they perceive. And so this last field is where I'm in, basically the perception of the world by an artificial system, and in this case, computer vision. So who knows what computer vision is? Okay, a few people, not too many, that's good. So I'll start by giving a very brief outline and sort of motivate the whole problem. Then I will tell you how Sintel can help, how Blender can help us, and then I will give a very brief outlook, sort of what is next beyond the current project. Okay, so to start, what is computer vision and why should you care? In the, well, highest level sense, computer vision is image understanding. So I have an image or a video sequence and I want to make some sense of it. So, for example, I want to describe what's going on, I want to detect objects, etc. We are not there yet. So instead we're going one level sort of lower and motivated by looking at three classical problems in computer vision. Optical flow, segmentation, and depth estimation. And so we start with optical flow, which is actually the main focus of this project. So assume you have two frames, such as these two frames, and now you want to, track the left hand of Sintel. So you get, you have like your small box, the patch surrounding the left hand in the first frame, in the second frame, and what you want to get is this motion vector. And so, the motion tracker of Blender can actually do this for certain sparse points. And what we want to get with optical flow are actually tracks for every single point in the image. So this is one possible representation with the little arrows here. It gets a little cumbersome, so instead we often look at images like this, where each pixel is color-coded according to its own motion. So the hue of a pixel is its direction, and the saturation is its magnitude. And here in the bottom right, you see basically the key corresponding the pixel motion to its color. So now don't be scared. Just very brief, this is sort of the formal definition of optical flow. We have a frame at time t, we have a frame at time t+1, and now for each pixel we want to assign the motion vector where this pixel goes. Now why am I telling you all this? Again, why should you care? What's the point? What can you use optical flow for? So one possible application is video retiming. So let's say you have you shot a video and you want to make slow-mo out of it. Or you want to change the frame rate without changing the speed of what's going on in the video. So in both cases, you want to do some sort of frame interpolation. And of course, you could just blend the frames together, have like a weighted average, but that usually looks really, really bad. And so if you have optical flow instead, you can just move every pixel by a fraction of its original movement to the next frame, and then you get a much, much nicer and smoother sort of frame interpolation. And that's actually how all the major retiming solutions work. Another application is dance tracking, of course, and that's pretty straightforward. Imagine a motion tracker like we have it right now, just sort of blown up for every single pixel, and you would get more data, and you could also get the data that you have right now just way more accurate because you have a larger area to integrate over. And the third application is image warping, where you take the motion from one video sequence and basically apply it to a different one. Why would you do that? Well, it is a nice visual effect. So here in this movie, What Dreams May Come, they used it to create this very painterly effect. So they actually took oil paint and sort of how that moves and flows and melts and applied that to the real video sequence to get this very dreamy, painterly effect. And well, they won an Academy Award for this. And it's actually my advisor's optical flow code that was used to generate this thing. So you can get something from it. So that's optical flow. Next up, segmentation. What is segmentation? It's basically grouping of pixels that belong to the same object. So from an image like this, you want to get something like this. From an image like this, you want to get something like this, and from an image like this, you want to get something like this. So you want to here the colors are just for visualization, but basically you want to assign indices to pixels, and pixels that share the same index sort of belong together. And why would you do this? Well, one huge application for this is object removal. So there was a lot of talk about rotoscoping, getting rid of stuff, either of full objects or of wires that, move your actors around and so on. And if you can actually nicely segment out these objects, then you can just do in-painting like it was done here, and they're gone. And it would actually make things really easy to sort of, or in terms of automating things when you could do that. Another example is selective color correction. So here, when you can accurately segment, for example, the shirt of this woman, you can apply a color correction just to this little piece of the image and, change the color of her shirt. And it actually works really, really well. So segmentation, that was the second problem. The third is depth estimation, and that is conceptually actually the easiest. So the task is basically what was also mentioned earlier. For each pixel, you want to assign the depth that this pixel has the distance that this pixel has from the image plane. So from an image like this, you want to get an image like this. So it's basically the reverse Z path in Blender. And what would you use this for in a scene? So one obvious application is this 2D to 3D conversion. So if you have an old movie and you need some money again, so you want to re-release it as 3D, get some more money, you need to sort of up-convert it to 3D. And this is a nice first step to do that and to get accurate 3D from 2D. So these are these three problems: optical flow, segmentation, depth estimation. And I hope I sort of motivated why computer vision or why progress in each of these areas can help the graphics and filmmaking community. And the point I want to make here now is that there's actually a way back too. That with Sintel, with software such as Blender, open source software, open source data, we can actually go back, and we as computer vision researchers can use results from graphics to improve our algorithms. So how does that work? Well, let's first look at optical flow. Imagine you are a researcher and you develop a new optical flow algorithm and you want to test it somehow, so you need to know how well does it perform. Well, there are standardized data sets out there for which the optical flow is known, such as this. So this is admittedly a little bit older, from 1994. So let's look at something more recent. Here, that's basically what is used mostly these days. And you can see on the left, sort of there are 2 frames, but they only differ very slightly. And so the problem is making these data sets is really, really hard, because you cannot really measure motion accurately in a real scene, which is why the scene is kind of simplified. It's indoor, it's mostly rigid objects, and they're only moving very, very sort of small amounts. Now, people have always been turning to synthetic data too, and then they get something like this. And this is, again, recent. And you can see the structure of the image is somewhat nicer, but it just doesn't look good. And the problem with this is that these data sets are made by grad students, basically. They're made by researchers. They are not made by artists. So the people who create these images set a little bit over the top, but they don't know what they're doing. They don't know how to create good-looking, realistic images with 3D software. And that's why you get synthetic images that look like this. So now, would it not be nice if we had a visual realism like this? And I mean, I assume you all know Sintel, sort of you know how it looks. It has, yes, it is not photorealistic, but compared to what I showed you before, it is much, much, much better. Much better. And the nice thing is that even though it was made by good people, it looks really good, we still have access to all the data. It is on the DVD, it is online. You can download the whole SVN server, basically, and have the true 3D structure of this world available. So now, what we did was we went ahead, took this data, and rendered the vector paths, because that is ultimately what we want to have. What is this optical flow? That is the vector path. And it looked reasonably good already, just straight away. There were a few problems, though. So one of this is that. On the left, you see the original rendering of Sintel, and on the right, you see the corresponding optical flow. And you see that the extent of the hair is way, way, way bigger in the render compared to the optical flow. And the reason for this is transparency. So if there is a transparent surface, Blender actually assigns the motion of the first opaque surface that a pixel hits. And that is why all this nice transparent hair feathering away is just ignored, and the hair is so small. Okay, well that's a little unfortunate. But we have a convenient Python interface, so we just wrote a script, remove transparency from all the scenes, and then this is what we get. It looks worse, it looks more cartoony, but it corresponds much, much better to the optical flow that you see on the right. And so now we did this, we ran it over all of Sintel, rendered it, it looked better, and then we looked at slanted surfaces. And is it, oh yeah, so and here you can see on the ground that it's just one flat plane, and it should move very smoothly. But you see these little jagged edges. It's almost as if you can see the triangulation. And so this is the error, red means higher error, to what would be the true triangulation. And the problem with this is that the way in which these motion vectors are computed inside of Blender is actually that it's computed for every vertex, down projected to the image plane, and then each triangle is filled or interpolated on the image plane in 2D. And that causes these artifacts. Okay, so no amount of Python hacking could fix this for us. But, well, you know, it's open source, so we can just go in and hack the motion pipeline. And that's what we did. And so now this is our final result, where we can actually see it's nice and smoothly interpolated, because now the interpolation is all done in 3D. And so these are just two modifications and hacks that we had to do to make this data actually usable for optical flow computation. And then this is the final result. So on the top, you see the images with all of our modifications included. And on the bottom, you see the optical flow fields. And so one thing that you can see is there are a lot of very saturated pixels, which means that there are a lot of large motions, which is good. We want that. You can see there's a lot of non-rigid motion. I mean, Sintel's running around and jumping all the time, and yeah, rolling. So these things were not there in datasets before. And the sequences itself are much longer. So instead of 2 frames that we had before, now we have sequences that are 50 frames long, so about 2 seconds. And so we generated all this data, and we provided for download. We published it last fall. And this is a screenshot of our website. So what happens is we put it out there, people download the images, compute the optical flow with their algorithms on these images, send it back to us, and we compute errors of their optical flow and then rank them. And so here we get a nice table of basically quality of algorithms. And this is being used by the computer vision community. So people from MIT and Stanford and companies in Japan are all using this to test their own optical flow algorithms. And I think it's very cool and very important to know sort of to the Blender community and especially the Sintel team that, you know, this stuff is being used beyond the original intent. So again, the submission system, the data, 2 technical papers that describe this are all available at mpi-sintel.de. Now, how do these algorithms actually perform? Because so far I've only shown you the true motion. Now let's look at what is currently the world's best algorithm for optical flow computation. So these are the motion fields we want to reconstruct, and this is the computed motion. So actually, when you look at other optical flow algorithms, this is really good. So you see, you know, it gets Sintel kind of right, it gets the dragon sort of right. It almost, on the top frame, it even gets this large motion to the right of the dragon. But it still has problems with the boundaries and with the accuracy at boundaries. And that is good. So we want this data set to be hard, and obviously it is. So we think it can really push forward the field. Now, optical flow was the largest part. Somewhat smaller, the segmentation issue. Again, to remind you, the segmentation task is to group pixels together that belong to the same object. And so Blender has this convenient pass called object index. Can't we just render that out and use that? Well, here's a result of this. And we can see here on the left, it actually works really nicely. So in this basket, all the fruits are properly segmented. You know, the objects are kind of nice. However, if you look at this, you can see that it actually the background gets merged together. So these wooden planks that are leaning against the shack just, get all mushed up. And the problem here is that this is inside Blender, sort of in the Blender logic, it is one big object scene or background or set. I don't know how it's called, but it's one big object. And that's kind of a problem because then it gets the same index. And now this leads to a sort of philosophical problem almost. So what is an object? It's not really well defined. Am I an object? Is my shirt an object? Is every button on my shirt an object? There is not really a right answer to that. And so segmentation based on objects is a little questionable. However, inside Blender, materials are actually well defined. So every pixel has a given material. And so what we do is we create an over-segmentation where 2 pixels get assigned the same index or get grouped together if they share the same object ID and if they share the same material. And so this is what we get when we render it out. It's what we call a cartoonified Sintel. And basically here you can see sort of these very flat surfaces that get grouped together because they share one object ID and one material ID. We haven't released this yet, but we've shown that to people who work in segmentation, and they're pretty excited about that. So that's going to be cool. And now the third problem, depth estimation. And this is actually the most straightforward because, well, as you know, we already have the Z-pass in Blender, and for our purposes, it's actually really good. So here is the uniform scaling, which is why some scenes are white because they're all very close to the camera. But yeah, I mean, you know how depth maps look like. What we can do with this now, though, is create something like this. And so here we have only the depth map and the image. And you should note that the camera is actually at the very, very top and looking down. And so we can reconstruct a 3D point cloud from a scene and actually have it as, almost as a 3D object. And now we can do segmentation with it and all kinds of other things. So to recap, we use Sintel to create data sets for motion estimation, segmentation, and depth estimation. And to stress that again, it is really, really fantastic. It's amazing that we have this rich 3D data set that looks good, and we can extract all this data from it. And so Sintel provides better data sets, and ultimately these better data sets lead to better algorithms. And this is why it's this two-way loop, because now we have better data sets, we can develop better algorithms, and that will in turn feed back. Now, what is next? Just very briefly, we have only sort of touched the very surface of everything that is inside of Sintel. So, of course, we can extract much more data, so we can extract the colors, materials, we can extract shading information if, for example, we want to learn how to estimate where a light source is. We can extract a number of more higher level information, so if we want to know whether a certain pixel belongs to a barrel or not, we can do that. We can also modify Sintel and re-render parts, so we can just move the camera around and render Sintel in stereoscopic. So if you can cross-fuse, I would recommend doing it here. It's actually a really, really cool effect to see these scenes in 3D. That's another thing. And then we can, of course, also freeze the whole scene, make it static, and just let the camera move around. So this is very, very much work in progress, which is why you have these texture errors on the person, and there's like a head floating around and these things. So, but it's just an example that we can, make the scene static, freeze it, and just have the camera move around. And the last point is, of course, beyond Sintel. I mean, it's great, but it's limited in its ways. So what we think about is visual realism, sort of how to make these synthetic images closer to the real world. And one way filmmakers have approached this is just by, integrating the real world. So, you combine CGI elements with real world footage. And that's, for us, not really usable because, again, from the real world footage, we don't have any true 3D structure. Well, but then there's also stuff like this. And that's what I want to end on. This is from LuxRender, completely synthetic. And if we have a 3D movie that looks like this, then computer vision will go crazy. And with that, I want to thank you for listening. I want to thank especially the Sintel team who worked, who provided this data set. Computer vision really owes you. Thank you very much. So, are there questions?
We have time for 1.5 questions.
Oh.
We have now time for 1 question.
Where we can, there's a way we can have the corrected vector pass with the correction you did to obtain a perfect vector?
Yes, so that's online. You can download these optical flow maps, and that is basically the vector pass.
No, I mean you correct with the code. To use to generate a vector pass in other scenes. Yeah.
So you can do that, of course. So the Python stuff is pretty easy. The Blender modifications we had to do, we did not resubmit that as a patch yet because it was based on the old Sintel, on the old Blender version that was used to generate Sintel. I don't know how this motion pipeline has changed sort of in newer Blender versions, but I'm certainly happy to talk about that, whether it would make sense to integrate that into a newer version.
Okay.
Okay. Thanks.
Good. Then thank you very much.
Yeah, thank you.
So quick question for the next presentation. Is anyone available to borrow a mouse? Does anyone have a mouse who can borrow?
There is a mouse here.
Oh, okay. Good. We found the mouse. Thank you. Good. I didn't know if you were...